Okay, so let me do a little bit of a review on what we covered last week. We barely got started on physics, but let's do a bit of informal review of what we talked about. Day one, we talked about what physics is. And you can even still see this. This is on this slide right here. It is the study of energy and matter and how they work together. If you guys recall, matter is our stuff. It's anything that has space and weighs something, right? You and I, we're all matter. But how am I moving? That's energy. And that's what we're going to talk about in physics. We're going to talk about like how things become in motion. So our first topic was basically an overview of energy concepts. And then the second topic on measurement, I didn't fully finish it. I wasn't sure I would on a short Friday. But our goal was to be able to talk about values. And this word was wrong. It's always wrong in my notes. We don't want qualitative observations. We want quantitative observations. We want to be able to put some numbers to things. This is crucial that we do this properly. So that's why I want to take some time before we actually get to like the formulas and the math that we're going to get to. I want to make sure that you get the concepts that you need to know about how to manipulate numbers. Okay. So I won't go through like the entire lesson we did on Friday, but we spent some time talking about how to convert up and down on the staircase. So hopefully this is a skill that like you're somewhat familiar with. And if you're not, make sure you ask me, okay? Like when I go around and I say, hey, do you have any questions? Ask, right? That's why I have a job. Okay. I didn't actually do this slide right here, so maybe I'll just do one of these ones real quick. If I gave you 5.6 kPa, and I want you to convert it into PA, all you have to know is what the prefix K means. And if you go back on the previous slide, or 2 slides ago, K is a kilo, it is 1,000 of something. That's all. So what you could do is you could just literally replace 5.6 kPa with 5, oh goodness, Chris, it's Monday morning, 5.6 times 10 to the 3 PA. The K gets replaced by the number 1,000. And if you do that, we'd actually have this number instead. It would be that many pascals. So that's kind of a short example. If you get what I did there, that's awesome. If that was like, Chris, I don't know what you just did there, that's fine, right? We'll just make sure I help you at one point. This one right here also involves a K, but rather than timesing by 1,000, if you're going from a joule into a kilojoule, you'd actually have to divide by 1,000. So anyways, that's one thing we talked about. Another thing we talked about is the scientific notation concept. Sometimes the numbers that we work with are so large or so small that it's kind of ridiculous to write them out. And so we use the shorthand notation, right? Like this 149,000,000,000,000, right? We would write it differently. You'd probably write it as something like this: 149 times 10 to the 9, and just move it 1, 2, 3, 4, 5, 6, 7, 8, 9. That would work. You could even write it as 1.49 times 10 to the 11 and move it over 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and put the decimal place kind of between those numbers. There's not one right way of doing it, but you just need to know that we often utilize this to shorten up numbers. So again, if you're confused by this, if I lost you at some point on this stuff, can we chat more later? One of the analogies that I've been given for teaching, I think this works well, is it's like bowling. When you're bowling, you try to knock down as many pins as you can. That's what I'm trying to do right now. In a large group, I'm going to try to teach to all of you at once. I think this is actually the least effective way of teaching. I think it's way better if I can talk with you in small groups. But like in a time like this, I'm just trying to knock down as many pins as possible. And if you get this, that's great. And if you don't, then just ask me later, and we'll try to pick up a spare if you like the metaphor. So we did some examples on that. And then we got to measurement uncertainty, and we talked about accuracy and precision, which is words we've also discussed before. Accuracy is like, are you doing it properly? Precision is, how zoomed in can we be? And this is actually really critical in physics because we need to round. Some of the numbers that we take are going to need to get rounded at some point. And this is where I think I lost a few of you last day. The idea of the sig-dig rules. So I'm going to try this one more time. And again, if it still doesn't make sense to you as I talk to the big group, then ask me and I'll try to explain it in like a one-on-one or a small group setting. So I want to start with an example and see if this helps make sense. Let's say that you took a measurement. You measured a weight, for example. You measured how much something weighed. And you got this number here. You got 10.6 .001432. That's how many grams something weighed. Wow, that is incredibly precise. But let's say that I told you needed to round it. Okay, like that's just too many digits. I want you to round it. And so I told you to round to the nearest tenth. Where would the tenths be? Well, the tenths would be right there. Does that make sense? Because this is your tens, this is your ones, this is your tenths. So if I asked you to round it to the tenths, it would be 10.0. And a question we might ask then is, how many digits do we have left over? How many? We call them significant digits. And the answer would be 3. Because I measured this number right here. I measured this number right here. I measured this number right here. I know some of them are zeros. That's just by random luck, they just happen to fall right on zeros. Right? But I would say this by our definition of rules, this has 3 sig digs. Would we ever write this number as like 0, 0, what 10.0 though? Isn't that kind of ridiculous? Because we don't actually put like zeros in front of numbers. Okay? And by that logic, any zeros that go this way in front of a number, those don't really count as sig digs. But any zeros that go this way, they do, because we took the time to measure that precision. And it just happened this was a 0. When I was making up numbers, I just made up random digits. Yeah. Good question. So here's why. Maybe I want to keep a little bit extra precision. Let's say it's not just 10, but it's 10.0. I know more information about it. In the same way on this ruler here, that this top ruler here, I know that it's for sure 1, but I'm not really sure what the next digit is. But see how this ruler right here, now I know that it's actually 1.2, and what I'm really uncertain about is like this, I know it's 1. And if I had to look at the next number, I'd guess maybe it's 1.2. But on this ruler here, I know it's definitely 1, I know it's definitely a 2, and I think it's halfway in between, so I might say 1.25. Would you say that this number right here is like a better number than this one up here? Well, with that same logic here, I could write it as 10, but 10.0 is more exact. Does that make sense? Now, you're actually maybe leading into one of the things I want to discuss. The number 10 is also problematic, though, because if we did write it as the number 10, I don't actually know how many digits it was rounded to, because 10 could have been rounded to the nearest ones, or it could be rounded to the nearest tens. Okay. 10's not a great example, but I'll pick another one like it. Let's say I gave you the number. Let me give you 3 numbers here. Let's say I gave you the number 269.157. Let's say I gave you the number, let's say 304.213, and I gave you the number 300.104. Here are 3 different numbers that hopefully you'd agree, they are quite different from each other. Okay. But depending on how I round, I could actually round all 3 of these numbers to the same digit. Let's take this last one here. Let's round this number right here, the 300. Let's round it to the nearest ones. So if I rounded this guy to the nearest ones, that means I'm rounding this number off, and this number off, and hey, this number's 300. Does that make sense? But keep watching. Let's say I took this number right here. Let's say that I rounded it to the nearest tens. If I rounded this to the nearest tens, I'm going to round this off here. Now, if I rounded it to the nearest ones, it would be 304, right? But if I rounded it to the nearest 10 grouping, 304 isn't quite halfway there to go to 310. So this number would also round to 300. And what about this top number here? If I rounded it to the nearest ones, it would round to that number. If I rounded it to the nearest tens, it would have been 270. But what if I rounded it to the nearest 100? Well, then it would turn into 300. Well, this is the problem with writing a number like this, 300. I don't know how precise it was. I don't know what it was rounded to. So to the best of our abilities, we really try to avoid writing numbers that end with zeros in this way here, because there's uncertainty to it. Add a 0.0 behind it though, and all of a sudden now I've stopped that problem. Now I know for sure, if I take the time to write these numbers right here, I know that I did round this one to the nearest 100th. Does that help answer your question a bit? Okay. Long story short, there are 4 rules we need to memorize for how we're going to count digits, because rounding is going to be a huge part of what we do. We're going to take a lot of numbers, and we're going to add, subtract, multiply, and divide them to each other. and we have to round at some point. So if you want to know your significant digits, here's the rules. If there's ever a number between 1 and 9, that always counts. The question is, where should zeros count? So if you ever have a 0 between 1 and 9, that counts. Like, for example, the number 109. This means you have 9 ones, no 10s, and 1 group of 100. We would say that this has 3 digits. If you ever put a 0 to the right of a decimal point, like 109.000, this just means we're zoomed in more. If you like my analogy I gave of us trying to find the Eiffel Tower that one day, if you can zoom in even more and more and more and like get a closer look at something, that's what this is doing here. This would now have 6 significant digits. But if you ever had the number 0.00013, I could keep writing zeros over here on this side for forever. And so these guys right here, they're just placeholders. These zeros don't really mean anything all the way up till here. So this number would have 2 digits. We'd count this one and this 3. Yeah. Like these ones right here, huh? Oh, those ones there? Okay. But only if we're measuring that precise though, right? Because we don't necessarily have the ability to find the next digit. For example, on this ruler right here, what digit do you think comes after the 2? And what digit comes after that? And what digit comes after that? Although I agree that we could keep going on and on forever, I don't believe that this is 1.200. What would the odds be that, like, as you measured this thing right here, that it was exactly 1.2 exactly? Isn't it more likely that it's probably 1.2? I'm just picking numbers out of the air here, right? Wouldn't it be 1.219372? But like, my measuring tool here does not have the ability to be that precise. Does that make sense? So we cannot add digits afterwards unless we're certain of them. I gave a silly analogy the other day, but I'll use it again. If you were to ask me how old I am, I could tell you that I'm 33, which is true. But that's not very precise, right? That's very generic. I could tell you, though, that I'm 33 and 5 months and 4 days and 3 minutes, right? And each time I do that, I'm adding like an extra digit behind. Does that make sense? But like, I'd have to have the ability to measure that, right? And some things I don't have the ability to measure that, right? I don't actually know that that's how old I am. I'm just taking a guess. You get what I'm saying there? So that's why numbers that come afterwards are very important, because they add more clarity and zoomed inness to your numbers. But you'd actually have to know them. Okay. Yeah. This one or this one? This one. Okay. This guy right here? The one below. Okay, this one here. Okay. No, they're only significant after you start recording digits otherwise. So like these 3 digits right here that I've pointed to right here, they don't count either. Because they're also placeholders. In a way, you have no millions, and you have no 100,000s, and you have no 10,000s, and you have no hundreds, and you have no ones, right? That same logic still applies here. You have no tenths, you have no hundreds, you have no thousands. So if we didn't count these ones here because you have none of them, I know there's a decimal point here, but like really that same logic applies. Before we actually started measuring something, like this is the first digit that I was actually able to measure something of, right? And so these ones here are also considered to not really count. Yes, yeah. So like these ones here, they do count because we've started recording some digits, but these ones right here, they don't count for these ones right here because we haven't even started recording numbers yet. It takes a little while to like figure this out. This is one of the reasons why I like my bowling analogy. If you want, we can chat about this more later because this is a weird concept. To some degree, if you can just memorize rules, you'll be fine. Like if you can just memorize the rules I tell you, it'll work. But if you want to discuss this more, we totally can. So if it's okay though, I kind of want to move on a little bit here. And I want to talk about some mathematical operations. This is where I left off last day. I think this is a good illustrator of like the idea of rounding. What we have here is 2 different measurements. And one of the measurements was taken on an exceptionally precise scale. Apparently, we were able to measure to like the nearest trillionth or something like that of a kilogram. That is like an incredibly precise scale. And then we have a different number that was measured on like a really crude scale. It only measured to the nearest tenth. I want to give you maybe a different example of this. Imagine that you stepped on the bathroom scale. Your bathroom scale probably measures either to the nearest pound, maybe to the nearest tenth of a pound. That's my guess. So like, pretend this is Chris, because I don't want to pretend it's one of you guys. This is Chris stepping on his scale. This is not a really good diagram of me. There we go. That is Chris. And I step on my scale. Chances are it's going to say something like this: 100, this isn't what I weigh, by the way, 186.1 kilograms. That's probably about as precise as it's going to be, right? Imagine then that I accidentally was sweating at the time. I just finished working out, and one drop of sweat fell off of me. Do you think the scale is really going to change in that case if I were to lose one drop of sweat? Because really, the amount that I'm changing is so minuscule that it's really not relevant. It's kind of the same analogy right here, is that I know all of these digits right here were very, very, very small incremental amounts. But compared to this number right here, which kind of had to stop right there, it really doesn't make a difference. I can't really count these digits here because I don't have something else to add them to. I wasn't able to measure how much further those were. Now, let's say that I was on a scale, and the scale I was on was 186.1, and then it was able to keep measuring my weight. It was 1, 3, 4, 5, 9, 2, 3, and then I lost one drop of sweat. And so if I were to subtract 0.00001, now could I actually effectively subtract these numbers from each other? Sure, but only if the scale was actually able to zoom in enough to get me more preciseness. So the rules we have for this one right here are pretty straightforward. Okay. If we're adding and subtracting numbers, we always round to whatever the least precise number was. And so since this number right here cuts off at the tenths, we got to cut the other number off at the tenths as well. So the answer to this would be 18 and 2 makes 20. 2.2 and 0.2 makes 0.4. But what would actually happen is that because I know this digit right here, at least since I know the 6 was above halfway, we would round it up to 20.5. But that's as precise as we can be, because I don't know what those digits were afterwards. My tool was unable to measure them, and so I'm going to have to keep it rounded here. And that's what happens a lot in science, is that we have to know when do we have to round the number? How much do we actually know? And how much would we be guessing? Because if I were to write the 6, 7, 9, if I were to write all of those numbers afterwards here, they may not be right because there were digits after the 2.2. I wasn't able to find them. So it could have been a 3 and a 7 and a 1 and a 4 and a 7 here. And if I add those up, well, now these numbers here would be wrong. The second thing we need to do is one like this. If we take two numbers and we multiply them by each other, we need to round at some point. I actually want to change this. Rather than multiply, I think it's even more extreme if I show you divide. Just if you have a calculator nearby, take 3.8 and divide by 14.6. If I were to divide these, here's what I got. I'll pause for a sec so you guys can do it on your calculator. That's where my calculator stopped. Now, depending on your calculator, it may actually give a slightly different number. I'm peeking over Isaiah's shoulder here. His actually gave 26,027,3973, and Isaiah's actually stopped right here, and it cut it off there instead. And maybe your calculator rounds to a different spot. The question then is where do we round these numbers? Because this number, do you guys understand that this number keeps going on and on and on for forever? And so we can't keep every single digit. We need to round at some point, right? Depending on how many digits your calculator decides to give up at. So the rule we have here is whatever has the least number of digits when you multiply or divide, we just stop there. So this 3.8 has two digits, right? A 3 and an 8 were both measured. Are there digits that could come afterwards? Yes, but only if we had a better measuring tool to find out what the next digits would be. And this right here had 3 digits worth. The 1, the 4, and the 6 were all measured. So what's the smaller between 2 and 3? 2. So when we're done, we need to keep 2 digits. So I'm basically going to start rounding this number by hacking off the back part of it here. And the question is, when do I get to 2 digits? And the answer is right here I have 3. This is 3. This 0 in front doesn't count. It's just a placeholder. This 2 counts. So that's the first measured digit we have. This 6 count, that was the next measured digit we had. This 0 was actually just, there's a 1 in 10 chance that it's going to be a number like 0 as of this point here. So it just happens to be a 0. But I don't get to have 2 digits or 3 digits, I get 2. So I guess we'd stop there. And this would be how we'd round our numbers. Hopefully the more we do this, the more it'll make sense. So like I said, if you're still kind of confused about this right now, don't stress. Okay, like we're just starting this concept. If I were to use the analogy of, I had a house of construction on that one poster I mentioned earlier. The first time that like you try to like lay some tile or you're trying to lay floor, like if it's not perfect the very first time around, that's okay, right? Like get some feedback, get someone to help you, and we'll get there. So don't stress if you don't get it right this second. Okay, this is I think where we got we ran out of time last day. So let's pick things up here then. Now that I've done some introductory kind of concepts, now what I want to start doing is introducing you to some of our main calculations we're going to use. And here are the 4 we're going to utilize in this unit to start off. The first one is distance. We might need to measure how far something is. And we have 2 different words for it. One is distance and one is displacement. And I'll talk about both of those a little bit later, but that's basically how far something goes. We can also talk about how fast something goes, and words we use there are either velocity or speed. Acceleration is how fast you can speed up. Okay. You ever heard like the phrase, the car goes 0 to 60 in 2.2 seconds? That's just acceleration. If I have like a fancy new sports car, and I want to get it up to highway speeds, if I'm stepping on the gas, it goes, and I accelerate really fast. But like maybe my old 1980s Volvo, which is a little rickety, like it can get up to 100 kilometers an hour. But like it may take a little while to get there. One has just a faster acceleration, but they might be both going the same speed and stuff. And then hopefully time is pretty self-explanatory. It's how long something. So these are some of the things that we're going to work on measuring in this class. Next week, Monday, when we come back from our kind of little break, a couple days there, when you guys come back Monday morning, I'm going to hopefully have some Hot Wheels set up in the hallway, and we're actually going to measure how far, how long it takes, and how fast the Hot Wheels are going to go as we race them down the hallways. We'll take some measurements, and we'll do a lab on this. One of the things we need to discuss then is why were there 2 words we use? On the previous slide, I gave you word displacement and distance. And I also gave you words of velocity and speed. And you guys were too polite to jump in and say, Chris, why are there 2 words? Well, I've got that on the right slide. Why are there 2 words? Well, it depends on how much information you want to give in your measurements. And maybe the best way I can do this is give you an example here. If I told you that you traveled 100 kilometers, or if I told you that you traveled 100 kilometers east, wouldn't you guys agree that the second statement here gives you a little bit more information? Because it tells you which way you traveled. The word we use is scalar. Scalar means that you only just give me a number. If I tell you that you had 17 something, 17 is just the number. But if I said that you went 17 meters to the northwest, well, now that's called a vector. Because vectors tell you which way you travel as well. And sometimes direction matters. For example, let's say that you were asking, how do I get to the office from here? And if I told you, you need to go down a flight of stairs, and you need to walk about 150 meters. I could have actually had you end up outside. Because you could have went down the flight of stairs and opened the doors. Does that make sense? Right? But if I tell you you have to go that way, and then go down a flight of stairs. Well, now as soon as I give you a direction, that's a little bit better. That makes sense? So there will be times when all we care about is just a number. But there will be times where we care about a direction as well. So we have different words for them. Oh, why are we not going forward here? There we go. So when we talk about measuring distances and displacements, I need you guys to use the right vocabulary. If you ever talk about a distance, all we care about is just the length. So if I were to ask you, how far is it from here to the wall? If you said, thank you. If you said that it was 7 meters from here to the wall, that's a distance. If I said it was 7 meters that way, like north or something like that, now we use the word displacement, okay? Because it also includes the direction. And one of the subtle little things that we're going to use in physics to help differentiate the two is like they're both going to get the same letter. D is the letter we use for this. But if you ever put a little arrowy thing on top of it, you guys see this little, I don't know, triangle a little bit here? It almost looks like the angle symbol. This symbol right here indicates that you need to include a direction. So I'll write that out here. Include a direction. This is a really, really basic formula that I want to use just to kind of to build our way into this. Has anybody ever seen this triangle symbol before? Do you know what it means? Yeah, it means delta. That's actually the Greek letter. The word is delta. And the Greek letter, what it means is it's the change. Whoops. Need some help there? I can get to it. It's how much change there is in something. And so sometimes what you need to do in order to calculate the change is basically just subtract two numbers. Okay. Let me give you a basic example. I have a daughter who is 4, and I have a daughter who is 6. What is the difference? What is the amount of time between the two kids I had? Well, you'd say 2 years, right? I have a 4-year-old, I have a 6-year-old, right? What I'm really doing here is I'm doing the change in time between my two kids. If I take my 6-year-old's age and my 4-year-old's age and subtract them, there would be 2 years of change between my two kids. Right? So sometimes all you have to do is just subtract a couple of numbers to figure out how much change there is. Okay. That's what this formula right here kind of describes. Okay. I want to use this analogy here, though, to help explain the idea between distance and displacement. Imagine you were driving from Edmonton to Peace River. If you were to be driving in red, red is the highway. And so here's the highway, and you're kind of going all over the place. Sometimes you're going north. For a little while here, you have to like turn and go directly west. Right? Sometimes you're even going east, you're almost backtracking. But let's say you were able to fly. Let's say hypothetically you're a bird, and you could just like fly in a straight line here. One of these two things would be the distance, and one would be the displacement. Now, before I give you the answer and before you kind of figure it out for yourselves here, I want to remind you which one is which. Distance means you cannot give a direction. But a displacement is a vector. It means you must give a direction. Which of these two methods here could we give a direction for? The straight line one or the curvy line one? Which one has a consistent direction? Yeah. So the one that would be the displacement would be this one right here, because I'm always traveling the same direction. I could tell you that the displacement is like northwest, for example, because I'm always traveling northwest. Does that make sense? But if I were to talk about a distance, the distance would be best described as this one right here, because if I were to ask you what direction you're traveling, well, it changes, doesn't it? Sometimes you're going north, sometimes you're going west, sometimes you're even going east, right? During this little section right here, you're actually even going the wrong way, right? Look, right here, you actually went too far. You had to like backtrack to get to Peace River. So whenever we have like a road sign on the side of the road, that is the distance you have to travel, because you're always going different directions. But a airplane that hopefully is going in a straight line, it would travel according to a displacement because it always is going the same direction. Hopefully. Does that make sense? Okay. Let's try a really, really simple example here to kind of start. I'm actually going to walk to the front of the room to like be like a demonstration. Imagine that you had a person. So I'll start here. I'm the person. And I'm going to walk 3 meters east. Ready? Here, I'm going to go 3 meters east. 1, 2, 3 meters to the east. And then I turn around and I go 5 meters west. 1, 2, 3, 4, 5. Okay. So here's my question. What's your distance and your displacement? Okay. They're actually going to be different values. Distance, we do not care about direction. So direction does not matter when you do a distance. So here's the answer for distance. Distance, I would say D is going to be 8.0 meters. Because isn't that how far I walked, right? I took 1, 2, 3, 4, 5, 6, 7, 8 steps. I took 8 steps, right? And I didn't care that I turned around halfway before. So my distance would be 8 meters. Let me give you the answer for displacement now, though. We would say that the displacement is going to be 2 meters to the west. Why is there a difference between the two? Well, let's consider where I started. I started here, right? I went 3 this way. Then I went 3 back. Well, not back to where I started, right? But then from where I started, I'm 2 steps to the west, right? Displacement, we care about where you started to where you finished. So in displacement, all I care about is how far you've like net moved, if that word makes sense, like how much net movement you have. So in one of them, direction mattered. This one right here, direction did not matter. I just counted up the total steps. In this one right here, I care about like where I started to where I finished. Okay, so let's try another example here. This one I'll go sit back in the back. Some of these are kind of like the math is pretty basic. I want to make sure you guys get the concept at first though. Let's say that James walks west from the school and Kate walks east from the school. So I'm just going to draw a brief little diagram. This can be school. And James is going to walk west. So we usually use west this way. So James, he can go 0.40 kilometers, and he went to the west. And Kate walked 0.5 kilometers, and Kate walked to the east. Here's why displacement matters. If I were to ask you what the distance between them is, hopefully you'd be able to say, well, the distance between them is this 0.4 and 0.5. The distance between them is 0.9. But if I ask you about the displacement, what we need to do is figure out where are you starting, where are you finishing? So the question here is, what is the displacement from James to Kate? So if we wanted to start at James and work our way to Kate, how far would you need to walk? Well, 0.4 plus 0.5 means you'd have to walk 0.9 kilometers to the east. Because to go from James to Kate, you have to go east. Well, what would the answer be if we talked about going from Kate to James, though? If you started at Kate and had to walk to James, the number would still be the same, though, right? Like, it would still be 0.9. But what would be different this time? Yeah, you'd have to go west. And so this helps maybe to illustrate a little bit as to why vectors are important, because sometimes we care about what direction you need to travel. If you had to somehow travel one direction there, and I gave you the complete wrong, like if you're supposed to go east, but I told you to go west, you'd end up in the completely wrong spot. So there are times where we really have to be careful as to whether or not we're starting here and finishing here, or starting here and finishing there. One more thing I want to point out, when I added these numbers to each other, what I was really adding was 0.40 kilometers, and I was adding to that 0.5 kilometers. Just to point things out, this one right here was measured with an extra digit. Apparently, James was able to measure his kilometers to like an extra digit's worth, whereas Kate wasn't able to. Her measuring tool wasn't quite as zoomed in. What matters then is that because James didn't know what the next digit was, this could have been 0.51, and it got rounded down. It could have even been 0.54 and got rounded down. So because of that, I have to like cut this number off at the 10th place, which is why I left it as 0.9, not 0.90, because I do not know for sure that next digit is actually a 0. I've got a couple of practice questions here. That was actually the end of the lesson. Why don't I just do 1 or 2 of them here, and then I want to move on to velocity, because you guys can try some of these by yourself. This is the exact same concept I just did. What we want to do is figure out the distance and the displacement that someone walked. So someone goes 12 steps north, then further north, then south, then north. Was that my door? Someone want to just grab the door there? Open it up. I didn't realize it was locked. Hello? Hi. Sure. So I'm just going to draw a quick little picture here. You're going to go 12 steps north, and then 15 more steps north, 35 steps south, 11 more steps south, and then back 16 steps north. So if I asked you for your distance, we don't even care about which direction you traveled. So all you'd do is you'd add all these numbers up. So 15 plus 12 plus 35 plus 11 plus 16 means how many steps did you walk total? I got a grand total for distance of 89 steps. And as a way of writing this, I just write it with D. D is the letter I put right here. And I don't put the little arrow on top because I don't care about direction. But if I want to tell a displacement then cares about like, well, where did I start? Where did I finish? Right? So as I kind of do this here, I've got 12 steps up and 15 steps up. It looks like I've gone up for a while. But then like most of this cancels out some more and then comes back again. What I really need to do is go like 15 plus 12 plus 16. That was all going up. And then going down, I had 35 and 11. And I got to figure out like, which way did I go more? Did I go more up or more down? So 15 and 12 and 16 means I went a grand total of 43 steps up, or north, I guess. 35 and 11 is 46 steps. So ultimately, which way did I go more of? I guess down or south, whatever that is, right? So what is my net amount? 3 steps, but then I need to include a direction. So we put like a square bracket behind it, and I would use, I guess, S for south to say that we went 3 steps south. And one cares about start to finish, and one doesn't at all. Does anybody have a Fitbit that like records how many steps you take? If you have a Fitbit and it tells you like how far you've walked over the course of the day, I would say that like if I have a good day, my distance traveled, hopefully I'm getting like 10,000 steps. What is your displacement though every single day? What is your displacement every single day? It's probably 0. Because when you woke up this morning, you were at home. And then you moved a lot over the course of the day. But as long as at the end of the day you went back home, you actually didn't travel any like net differences. Does that make sense? So like your displacement on any given day is actually 0. The distance you traveled was a lot, right? But the only reason why your displacement wouldn't be 0 is that if you like stayed somewhere else, like if you were staying in a hotel or you drove to Tabor or something like that, and you stayed overnight. Anyways, that's my lesson that I didn't get a chance to finish the other day. Did you guys have any questions you can think of right now? And I phrased it that way on purpose, the questions you can think of, because like we're not really doing anything yet. I'm just kind of introducing concepts to you. So, okay, I'll pause that there, and then let's